All right. Good morning, everyone. First, thank you for being here in this morning, and thank you for having me. I am loving this town. It's such a beautiful, nice town, and it's a pleasure to be here. My name is Vinicius Carvalho. People call me Vini. Since we're friends now, you can call me Vini too. And I work at Netflix and the video algorithms team. To break the ice a little bit, can I ask you, how many of you here have Netflix? Don't be shy. Oh, thank you. I hope you're not sharing your passwords, though. Okay. So what I want to share with you today is how we actually build our video encoding pipeline. So video encoding, for those who are not familiar, it's a compression process. So we try to get very big data compacted so it can actually be sent over the wire. And that's what I'm going to try to do here today in 35 minutes or so, show you a high-level overview of how Netflix does video encoding, as well as what is behind our infrastructure. It's called Cosmos. Throughout the presentation, I hope you can download the presentation later. I've put links for our blog. If you've never read any of our blog posts, I highly recommend you to. There's a bunch of information. We have a very active tech blog post. And most of the information here, you can correlate from there. Okay, so let's kickstart this. Or maybe no. Okay, sorry. All right, so the way I'm sorry, we're having technical difficulties. Not sure. I apologize for that. Yeah, I'm experiencing some lag of sorts. Just one second. I'm so sorry. I have no idea what's happening. Okay, finally, I think I got it. Okay. Well, live is tough. I tell you, we do live, and it's not easy. I don't know what's going on. Sorry, folks. If there's some network issue here. Okay, do we have a plan B? I don't know what's going on. Okay, thank you. All right. Okay, so apologies for that. Apparently, I'm having some issues with my laptop. Yeah, so thanks. All right. So I tried to break this in 3 episodes, right? So the first part, we're going to talk about how do we do things in Netflix, okay? How we actually do the encoding pipeline. Then we're going to take a look into the Cosmos infrastructure. I'm not going to go too deep in many of the topics. It's a lot of things to cover. But if you find me outside, come ask questions. I'll be more than happy to, take questions anytime. And then finally, we'll talk about some of the lessons we learned through the journey, right? I'm going to pretty much skim this. I've been at Netflix for 3 years. I was at Google before Netflix, and before Google was in the Spring team. So if you know Java, I was in the Spring Cloud Streams and Spring Cloud Data Flow team, and that's how I pretty much landed Netflix. I've been working with Java for 21 years, and just saying that out loud makes me cry. Okay, so who we are, right, at Netflix? So we are the video algorithms team, and we're pretty much responsible for anything that's pixel related, right? We say that we give you the best bug for your byte because we're all about video compression, okay? Within my team, we have folks like myself working in video image encoding. There's the production systems that, does the encoding, transcoding pipeline. And we also have folks on the video quality team, and those are researchers. They're always improving and advancing the technology. So for example, the Alliance for Open Media, which Netflix is part of, along with Google, Microsoft, and others, they're coming up with the AV2 standard, the codec, right? So some folks on my team are actually right now researching and implementing the codec as we talk. So Netflix video is pretty much, we touch 3 areas, right? So the only part we're going to talk today is the SVOD, streaming video on demand. You're used to that. You play whenever you want. We also have live. I'm not sure if we have live in Poland, so I apologize for that, but we do have Netflix live now. For example, we're going to have Mike Tyson fight in July. And we also have games. So we do have cloud games. We had a beta launch in North America. And the idea is that you will be able to play, you take your device, it turns into a remote controller, and you play a game on your screen. Right? So my team is responsible for the transcoding part. Right? So there's a team that does the rendering, the studios that develop the games in Unity, and then we take the pixels from there and we send to the TVs everywhere. Okay, so first thing, video is big data. Okay, just to give you an idea, this is Bird Box. The mastered video is over 600 gigabytes of data. The Irishman, it's over 1 terabyte, right? So there's no way we can send that kind of content to you if we don't compress that. But Netflix, big data is also at its scale. So on a daily basis, we run thousands of projects, okay? We use hundreds of thousands of CPUs at Amazon, and then pretty much they're pretty happy for that. We run hundreds of millions of jobs, so each job is a encode job, and we process several petabytes of frames. So, and that's on a daily basis. You might be asking, how come we don't have that many titles, right? And then hopefully will be, you understand after the first part. Very high level review of video encoding. By no means I want to try to explain everything that goes in video encoding. The link from this GitHub, if you can access, if you're interested in learning more about video codecs and how they work, highly recommend you doing that, right? But basically, video encoding is the process of compressing data, right? And it's a lossy process. So we do lose data while we do the compression, and our job is try to make sure that we don't lose quality during that process. And the way that we can reduce the size of the videos, there's a bunch of things that happens. There's chroma subsampling, there's transformations that happen, but mostly it's a spatial transformation. So we try to reduce within each frame the data, and then also a temporal transformation, so between frames. So spatial transformation, what we try to do is we try to predict the pixels around the other pixels, and we don't send those pixels over. And then temporal redundancy removal is we have this thing called a keyframe, that the frame that we send, it's the whole frame. And then the next frames, they can be predicted or by-predicted. And the way that it works is, if you see 2 frames here, they're pretty much the same, except the ball moves a little bit in the second frame. So the video codecs, what they will do is they only send the first frame, the keyframe, and then just the difference between that, right? It's actually not the pixel difference. There's motion estimations and more things that happen. But that's the whole idea, right? We don't have to send all that information over the wire. And that's how we can compress the video. One other thing I want to just mention, quantization, which is the process of reducing the precision of the encoded video. And I only mention this because I'll talk about this later and want to make sure that we have a general knowledge. So the idea is that once you have your transform matrix of the pixel data, you can apply a quantization step and you can reduce the number of data that you send. So as you can see, we go from, I don't know, 6, 8 pixels that we're sending to 3, because we're applying a step of 10. The higher the QP, the lower the quality, the higher is the compression ratio, okay? So let's talk about our encoding pipeline, right? How do we get from, the camera to your TV? And in a very compressed version as well, the topic of this presentation is compression after all. I'm trying to put in buckets here what we actually do in a simplified manner. So we start with source inspection. So we do a source inspection when we get the video from our studios or from third-party studios like Sony or Warner Brothers, right? We run a bunch of inspections. For example, that pixel or black frame detection. Then, once we validate that that's a valid source, we extract information from the source. I'll point out the crop detection and the shot detection. We're going to talk about why they're important later. Then we go into what we call a pre-encode stage. And that stage, we try to create the recipes that will actually encode that video, depending on the codec, depending on the resolution, and whatnot. Finally, we go into the encoding pipeline. After the encoding, we run some validations. We measure quality. That's very important to us. And then finally, we package and push to CDN. Okay, so we'll take a look into some of those steps here. The first one, after the inspection, sorry, so the second one, is that we run a bunch of analysis. And I mean, it's like a couple of dozen, right? And two important analyses that we run. One is the shot detection. So we have an in-house machine learning algorithm that inspects the video and detects shots within that video. You can actually run with FMPEG today. FFmpeg has a filter that will give you the shots with any video, right? And that's important to us because we want to know where are the shot boundaries and what are the frame ranges of each one of them. The next one, it's the crop detection. But videos can have letterboxing, pillar boxing, but we are really interested in the active picture region, right? So we also run crop detection on every frame, and then we get, okay, where is the active region for each frame? That also is important for us. It's important for players so they can keep the aspect ratio. Finally, we go into the recipe generation, right? So in that step of the process, what we do is for each encoding job that we run, we try to find the best possible configuration of a codec at a given resolution. And the way we do that, in a very simplified manner, there's links for our tech blog on this, is that we run pre-encodes with different parameters for the encoding process. Okay, so we do have heuristics that say, okay, we're gonna pre-encode this chunk with these arguments X, Y, Z, and then A, B, C, and then we keep changing. And then once we encode them, we get back the videos and we get the quality results, and we choose the best one. So that is the best, parameters for a video, and that happens that depending on the scene, that changes from time to time. So that's another reason why we encode so many jobs, is because we do like at least 3 encodes per chunk for each video. We have a ladder generation service that will select the best point. So the optimal point is not only the best quality, neither is the lowest bit rate. It's a combination of both. Okay, so we run a ladder generation service on that. The reason we do this is that prior to 2015, every single video on Netflix had the same bit rate. So we use fixed bit rate for everything. And then in 2015, we say, hey, it just happens that certain type of videos can have higher compression. For example, animation is really good at doing compression. Like as you can guess, pixels are very similar. There's not much noise. Usually there isn't much motion as well. So you can achieve a lot of compression and keep the quality. Action movies, for example, are in the other side of the spectrum. So we started doing by title encoding in 2015. And then finally in 2018, we expanded that idea for shots. And that's why the shot detection is so important to our pipeline. So for example, Jessica Jones here, the first scene might require a lot of bits because it's an action-packed scene. And you see the second one, she's just sitting in a room, static background, a lot of dark colors. We can go pretty high in the compression and still keep the quality, which is that's important part. So our ladder generation service will do this. For example, at a given resolution, we run multiple pre-encodes, and for each shot, we take the average and we plot this in what we call the BD rate ladder. And we keep doing that. And then a service will come and create a convex hull and find the optimal points. With those optimal points, it will create the recipe. And that's going to be the recipe we're going to use to encode, right? And that takes in consideration quality and size. I don't remember the number now, but I think Netflix is responsible for something like 15 or 18% of the internet traffic. So, saving a few bytes does help everyone, not only us. All this is because something called adaptive bitrate streaming, right? So this is possible because when you're playing, our player will negotiate with the servers what is the optimal package to fetch, right? So if you have a very steady internet, you always get the highest quality possible. But let's say there was a hiccup in your internet, your mobile phone, right? Instead of rebuffering, we send you a packet at a lower quality. People are usually more okay with a drop in quality than rebuffering. Rebuffering is really, really bad user experience. We don't want to do that. And then the encoding stage really is, this is pretty much a simplified version of what we actually do on the video encoding service. So once we fetch the source information, all the metadata around what's the source is, the colors, HDR metadata, crop information, shot information. With the shots, we have something called the splitter, which will chunk that. We do chunk-based encoding, which means that if I have 800 shots in a movie, I will actually have 800 encoding jobs running in parallel. Once those are done, it's pretty much a map-reduce type of thing. We have a video assembler that stitches everything. And then we run some validations. We want to make sure that what we encode is actually what we were expecting to encode. Right? And that comes now for you to understand why millions of jobs. So take a title. For encode families, the codecs that we mostly use, 5 resolutions, 10 QP values. And then if you simplifying, if we say that this is a 40-minute title and we're doing 30 seconds chunks, it would be 80 chunks, 80 shots. That's 16,000 encode jobs. The reality is it's way more than that. So a title like that will have something in the about 800 shots. And so that number is like 10 times bigger than that. And then you factor that we also do pre-encodes. So encoding an episode in Netflix is probably like 500,000 jobs that we run in parallel. All right, the validation stage, we finished. We want to make sure that things are okay. We do frame rate, frame count, check the syntax. Is it decodable? Can players actually play that? And then we, of course, test for quality. So VMAF is our metric. It's something that Netflix came up with. It's a video quality metric. It's pretty much the standard in the industry today. So we run VMAF on a title. We get a score. And then, again, we have heuristics that say, okay, for this given resolution and QP, are we in the acceptable range, right? If not, then we have to manually inspect what's wrong with that video. Packaging is the last step. So we get the what's called to-doom, that sound that comes, the main contact and the dub cards. We stitch them together as a single video. We apply DRM. We package the audio. We DRM them as well. And then text, some manifest, and then we send to S3. That's pretty much where our job as video encoding engineers ends. And then we handle this over to Netflix Open Connect. So it's our CDN. This chart here is from 2021. There were 17,000 Open Connect appliances in the globe. So when you stream Netflix, you're actually not streaming from our servers. You're streaming from an Open Connect appliance who's sitting in an Orange or T-Mobile, your ISP provider nearby you. Okay? And we do that, again, to reduce latency. And we don't want everyone going to the United States to try to download the videos. So on our IX sites, we have a bunch of IX sites in Europe, in America, and Asia, which are our own data centers. We pull that data from the S3 bucket, and then we push that data into the ISP sites on those OCAs, and then you guys can finally stream that on your house. So that's the last mile. That's where you get the data from. So that's the end of the first part. And now we're going to take a look into what is Cosmos, right? We're going to take a peek at Cosmos. And this is the article here is our blog post on how we re-architecture the video encoding service to run in Cosmos. All right. So what is Cosmos? It's a distributed asynchronous platform that orchestrates long-running and resource-intensive media pipelines. That's a mouthful, but it is. It's a bespoke architecture that we built in mind to run this number of encode jobs in parallel the way that we do. It's really media-centric, so that's one of the key features of Cosmos. If you look into a Cosmos service, also from the blog post, the idea of Cosmos is that everything talks through messages. Like our encoding jobs, some of them can take hours to complete. So there's no way a traditional request-response paradigm would work. So we use a proprietary layer called Timestone to deliver the message across the services. So each service talks through asynchronous calls. A service is usually an API, a workflow, and some functions, right? At the top layer here, Tapas and Sagan are our high-level workflows. They deal with the orchestration and doing everything, the audio encoding, the video encoding. So everything that's part of the packaging, they orchestrate the services. My team works on the video encoding bits. We have a sibling team that works on the audio encoding. And those workflows are then accessed by studio applications, like front end, and actually, human beings are interfacing with that. We have 3 layers. Optimus is our anti-corruption layer, the best way I can describe it. It's an API layer. Plato is our workflow. Plato started as a forward ruling engine, just like the JBoss rules, if you're familiar with that. And then it evolved into, not evolved, it actually added a simpler model that uses graph, because the rules were sometimes too complex for us for simple services, right? At the higher level, they still use rules, but at the lower level services, we use graph now. And then Stratum. Stratum is the workhorse. It's our function as a service. All the encoding jobs, everything, the ML, all the things runs inside those functions. Everything above it is just orchestration. Timestone, I ask my good friends at the Timestone team to come up with an elevator pitch. This is what they came up with. Timestone is a highly distributed priority queue with durability guarantees. There's a blog post, and I don't have time to dive into it. Please go and read it. But the whole idea is that other things like Kafka, SQS, RabbitMQ, they couldn't really fit our purpose, so we have to build something in-house for that. Another interesting piece of technology that we use is called MassFS. And MassFS is a FuseFS abstraction on top of S3. And I know there are already things like that, but we also have reasons why we built MassFS in the first place. The interesting thing about MassFS is that it mounts files that were in a block storage like S3 as file systems for the function developers. But they are lazy mounted. So if you SSH into a container and you ls the folder, you can see all the files. The file descriptors are there, but the files are actually not there. Only when you start reading the files, we start streaming those files. So you might be asking, why would you do that? Well, some of our jobs only require to read the first headers, the first bytes of those files, and would be very it wouldn't be practical to download petabytes of data when you only need megabytes of data. So that's why MassFS exists. Optimus, our anti-corruption layer, it is a Spring Boot app. You have a gRPC channel for external apps and users, but through Cosmos itself, all the messages fly through Timestone. So we don't actually call through gRPC, we go through Timestone, and it's actually built in a way that the client, the gRPC client, abstracts that from callers, right? So our gRPC client has generated code. Instead of just doing a gRPC call on HTTP2, it actually posts to Timestone instead. Developers are completely unaware of that, by the way. I mean, we all know that this is happening. We don't have to deal with that. Plato, our managed workflow execution layer. And this here is the view of my favorite part of Cosmos. It's called Nirvana. So Nirvana is our observability tool into what we can peek into everything that's happening into our systems. Here's a view of taking a look into the facts. And we call a fact pretty much anything that is an input or an output of the workflow layer. So if you think about a workflow, you have nodes in a workflow. Everything that gets passed and through nodes are actually stored, which are just the method arguments, and then we can peek on that at any time. This really helps us when you're trying to debug something. It's stored in Cassandra, by the way. So Plato, our seamless async execution layer, and I say that because all this asynchronous execution, if you're familiar with message-oriented middleware, right? We don't have to ask our developers to send a message, poll for that message, find a correlation ID. Was this message the one that I sent or anything like that? Everything works in what we call an action and a reaction block. So you annotate an action. So whatever you return, in this case, I'm doing an encode response because I'm calling the encoder function. If I have a reaction block, that encode response will go into that block. So Plato does all the orchestration, handles things like priority, scheduling, observability, all that for us for free, and we don't have to worry about that. And then when it gets into our container fleet, we get Zipkin traces into Edgar, we get logs into Radar, and we get metrics into Atlas. All that for free for us developers because the platform team thought about that. So this is all part of the ecosystem. As I said before, Stratum really is the workhorse, right? And it's a function, it's a serverless function as a service. So the first thing people ask me is, oh, why didn't you use Lambda? And I'm really glad that maybe a year ago, Amazon published a blog post where they say, oh, we stopped using Lambda on our video, Amazon Prime, encoding pipeline, and we saved 90% of the costs, right? So Lambda is really expensive, and they're not really tailored for a long-running process. So what we did was we actually built a completely function as a service on top of EC2 and Titus. So Titus is the container orchestration we use. We don't use Kubernetes. Titus is an open source project. You can check it out. You can use it if you want. It's really tailored for AWS. That's the gist of Titus. So it is an economical alternative. The other thing is the Stratum has specific contracts for media processing pipeline. So a Stratum function has things like media input, media output, video frame sequence, media document. So those types are actually internal types that we actually use and our media pipeline engineers are used to. So it's really tailored for media processing. We do have other uses for Stratum today in Netflix, but for most of it, it was built for media processing pipeline. Each Stratum function is a Docker container. We hide that from developers, but that's what it is. And we can actually have shapes, and I'll talk about shapes in a minute. So the whole idea is that if you're in your workflow, you work with things like frame sequence, recipe, cloud output, cloud input, and those are like abstractions, like the media abstractions I spoke about. Well, Stratum function will intercept that call and convert into things that you as a developer you actually need. So for example, your frame sequence, you say, I want to encode frames 0 to 120, right? It will mount the correct frames for you in the file system, and you as a developer, all you have to do is, you think they're local, but they're actually in S3. And then when you finish, you write your bit stream to the pointer of the cloud output, and Stratum will take care of uploading that for you. So developers don't have to worry about S3 or any of those libraries. We actually have a layer between S3 and us. It's called baggings. So even baggings itself, we don't have to worry about. The whole idea of shape sizes, it's because we build our own scheduler and we want to utilize the most of our EC2 instances. And in order to do beam packing, we also need to make sure that the instances are properly sized. So when you define your Stratum function, you give some sizes for it, you give a label. And in a very simple manner, if I have a low resolution in code, it's going to go to like a small instance. If I have a high resolution in code, it goes to a bigger instance, right? So we define those shape selectors, right? And all we have to do is put a tag in the request for Stratum, and then the Stratum platform will actually route to the proper container. Okay, and resolution is just one of the metrics that we use. Okay. And before we go, I want to talk about Master Yoda and his famous phrase, and do or do not, and there is no try. I'll tell you this guy failed distributed systems. Retries are so important. If you're familiar with bulkheads, circuit breakers, and all that, this is all baked into our platform. And just to give you an idea how retries are important, a couple of months ago, one of my functions had an incident where the networking team was switching from IPv4 to IPv6. I was completely unaware of that. It just so happens that my function was calling an IPv4 service and the route was not working. And on that day, I got a bunch of alerts, I got a bunch of messages, and I saw there was 10 million executions of that function, which is a spike where it usually go around 2-3 million executions, so that particular function. but the number of errors that users saw was only 6. So I didn't got ping in the middle of the night because the users, the studios, were not seeing errors. But then we noticed that, and then we start talking to the networking team. We found the root cause, and we fixed it. So yes, we had to do a lot of retries. What happened is, sometimes it would land in a container that was in an IPv4 region, and it would complete. It would land in an IPv6, it wouldn't complete. Very hard to find, but we shielded our users by doing all those retries. Not optimal, again, we're doing a lot of retries, but the important thing is our users didn't even notice. It was a blip, 6 errors out of 10 million. Yesterday there was a talk from the folks from Atlassian. I swear to God, I had this before. They were talking about Taylorism. And it is true. We can only improve what we can measure. We take this by heart at Netflix. Atlas is our it's a time series database storage that we built in-house because we collect trillions of data points in a year. It's also open source. Go check it out. So we use Atlas. We take metrics for everything. We have dashboards that show everything. I, of course, redacted the y-axis here, but we can see like the amount of CPU used, the containers, disk, connections, everything. And for everything, we have an alert. And everything gets sent to me through Slack. This is another view into Nirvana, on the observability part of Nirvana. So just to give you an example, this is a encoding job. Full encoding, all the services. Also, I had to redact the name of the services. But what we see here is all the traces, right? And the spans. This particular job had 101,000 spans, which means that 101,000 remote calls happening while this thing finished. And we can see everything here. If I click in any of those bars there, I can go to the service, and that's actually a span call. So some takes like 27 minutes, 1.5 minutes, 58 seconds, depends on the service it's invoking. But this gives us a lot of visibility, right? So when I click on a given span, I can actually go into the logs of that service from one click. If I want to see what were the arguments that we passed to the function, I can click in the invocation details, and then I see, okay, what was passed, what was returned. I can see everything. We do use proto buffers for everything. So we actually deserialize them as JSON, and we can output them. Another important part of information, we get the build number of the function. We build, I would say that each function we build like 4 times in a day, because our CI pipeline is always building whenever there is a dependency change. So anything that changes in our platform, there's a change, we build a new version, we deploy automatically through Spinnaker. So sometimes it's rare that can cause a problem. So having the build number is really important. So we have to, we can correlate, we can find what changed, what happened. And then we also have information about titles containers. So inside our team, majority of the code is Java and Python, but we also have a lot of C++. But the C++ code we actually invoke through Java, right? So we wrap the call within Java, and Java calls the C++ code because we get the benefit of here, Spring and all the observability, all the plugins, everything that we have. And sometimes there's out-of-memory errors, for example. So the container logs will give us to us, right? So we can inspect that. This is a look into our logging system. It's called Radar. It's an in-house product. We don't use anything like Elasticsearch or Logstash or any of that. But they provide very similar capabilities. You can filter, you can create metrics, you can view alerts, and you can view the timeline, dive into each line of code, see what's the exception trace and the function information and whatnot. Okay. Well, it was a lot, sorry. So the very last, what did we learn through that journey? So we've been doing this for 4 years now. And we did learn a couple of things I want to share with you. This is not all the lessons, of course, but some of them. So first one, again, source here from Atlassian, where I took the Conway's Law information. If you're not familiar with Conway's Law, it says that your architecture will mirror your organization. And this is such a perfect example. We have a 3-layer architecture. Guess how many teams we had developing that architecture? right? So we had 3 small platform teams, and we built a 3-layer platform. Now that has been like changed. We now have 1 single platform team. We are changing a couple of things inside Cosmos. Cosmos is always evolving. For example, we're merging the workflow layer and the API layer to make things easier for developers to use. But I thought it was a very interesting exercise in learning this. Second thing, don't drink from the Kool-Aid, honestly. Somewhere in our documentation, there was this phrase, sharing protos across the 3-layer is discouraged. So that comes from the idea of bounded contexts, right? But I think we took that on the wrong way. What we did is, okay, we have all these services and functions. They're all the same. They all need the crop parameters. And then we created 1 crop parameter for each service and a different package. We had to do type conversion every time we talk to each service. That was a burden. So didn't work out. I'm old enough to remember EGB and entity beans when they were still like 2.0. And I think we just took that to the microserver paradigm. It was a misinterpretation of the anti-corruption layer design. We since fixed that, domain-driven design. We created our bounded context called the video engineering context, where we define types that we share, and we don't have to worry about them. At the edge of each service, yes, we do have anti-corruption. We do transform them to protect ourselves, so we can, for example, upgrade a model without impacting the API. But that's only at the edge now. And the final one, so don't become a snowflake. And this, I don't think there's actually a way to fix that. Cosmos is a massive platform. It's a bespoke architecture that we had to build with media pipelines in mind. What happened is Netflix has its own platform, and we kind of drifted away from our internal platform. So for example, Netflix today uses a newer version of Spring Boot, of JDK, and we're still a few versions behind, and we're trying to catch up. I don't think there's a easy way for that, because as we're building Cosmos, we're also implementing and bringing all the video pipeline into Cosmos, right? So there was a lot of features being added. So now we're closing the gap, trying to crunch the technical depth and be close to our platform. I think that's the final lesson I have. I have 2 minutes. So there is okay, first thing I want to talk about, we are hiring. I'm currently interviewing a lot of folks. If your background is in media processing, please check this out. And yeah, maybe we can be, co-workers one day. So jobs.netflix.com, go check it out. Try to find the L5 video algorithms, and you're going to see what we're looking for. And finally, I think I have 2 minutes. Maybe we have time for some questions. I do have one thing I would like to ask you all, if you don't mind, is that I would love to take a picture of this beautiful audience, and I take this to Netflix and show with my team. So if you don't mind, I'm going to try to do my best here. And okay, let's smile. All right. Okay. Thank you, folks. I really do appreciate you being here. We have 1 minute and 30 seconds. Can we have, maybe if someone has a question?
About some numbers, like if you're processing like 1 movie, so like how much time you need from like putting this big chunk of video to the final product, like this whole version of it?
It takes a few hours.
Few hours.
Okay, yes.
And one more thing, cost of it, of the infrastructure, like for just like order of magnitude, maybe like $5 for processing that kind of thing, or
that information is completely confidential.
Okay, I thought you told out. Okay, thanks.
All right, we have one more over there, I guess.
Hi, you mentioned that you're hiring, but I can see that everything that you developed is in-house solutions. So, learning curve for the developer is steep, right? Don't you have a problem with that you don't rely on open source solutions like Elasticsearch you mentioned and stuff like that? That everything that it's in Netflix you need to learn because of Netflix, so you cannot share the experience that or developers have around the world, but for me to learn Netflix stuff?
That's a great question. And it's to a certain point, it's true, okay? But we have set things in place to help out folks and onboarding and process like that. We do use a lot of open source. We actually open source a lot of the things. But yeah, unfortunately, we have to build a lot of things because our use case is very specific. So I think I ran out of time, right? Okay. Folks, once again, thank you very much. It was a pleasure being here. I appreciate you being here today. Thank you.